Talk about some work I'm doing on a intersection of representation theory and category theory, and I'll try to make this talk pretty darn self-contained. So let me just get myself set up here. So let me start sharing my screen. So this is work that I've been doing with my grad student, Joel Moeller, and also with a old friend of mine, Todd Trimble, who's a category theorist, who is one of the brains behind the NLab. So there's this online wiki of information about category theory, and lots of articles in there are written by him. Lots of the better articles are written by him. So some people are very grumpy about the NLab because it defines some very obscure concept in terms of 5 other obscure concepts, and you feel like you're sinking into quicksand. But that's what math is like, right? But Todd has written some very nice sort of self-contained explanations of things on the NLab. So there are those too. So this picture here is actually a picture of a Schur functor in a particular way of drawing them. So it's a direct sum of Young diagrams is what we're seeing there. So let me sketch out the idea here. So the symmetric group is like the group of all groups. It's the best group. It's a bunch of groups. It's the group of permutations of the set of an element set, say the numbers from 1 through n. And people have spent a lot of time thinking about representations of groups on vector spaces. So you know how rap musicians talk about keeping it real. Well, I like to keep it complex because so I'm only going to talk about the field of complex numbers, but we could get more fancy, but let's keep it complex. So I'm going to look at representations of Sn on complex vector spaces, and it turns out that they are classified by pictures like this, which are formal direct sums of n-box Young diagrams. Pictures, notice these all have 5 boxes because I was doing representations of S5. So I won't explain the details of that so much, but what I want to say is that the category Schur is cooked up so that it contains representations of all the different symmetric groups. So a typical object of Schur will be drawn as a direct sum of Young diagrams, but they don't all need to have the same number of boxes. They can have any number of boxes. So the idea is that the representations of Sn for all different choices of n all get lumped together in this big fat category called the category of Schur functors, or I'm just going to call the category Schur. So what I want to do is explain some of the importance of this category Schur, and it's by the end of this talk, if I've been successful, you'll sort of understand this one sentence. The category Schur is the free symmetric tworig on one generator. Now you've probably, I hope, thought about things like the free group on one generator, or maybe the free abelian group on 2 generators, or maybe something even like the free ring on one generator. I don't know if you've thought about that. It's very common to cook up free structures where you say, I'm going to take an element, call it a generator, and then just start doing whatever I can do to it, given that I have a group or a ring or whatever, and freely build up all sorts of junk, not imposing any equations other than what I need to. But you can do that for categories too. So we can have a category that's the free something or other on one generator. So of course, I don't expect you to know what a symmetric tworig is yet, so that's what I've got to explain. But let's start off slower. Anyway, this is a theorem that's going to be in a paper by Joe and Todd and myself. But let's start out with something similar, but easier. So z of x is polynomials with integer coefficients on one variable x. And this is the free ring on one generator. So if anyone asks you why are polynomials so important, this is like a high-level answer. It's because the free form the free ring on one generator. What does that mean? It means that if you give me any old ring and any old element R of that ring, that there exists a unique ring homomorphism from Z of X to R that sends X, that element in Z of X, to R. And so it's easy to see the reason why. If F sends X to R, well, everything in Z of X is some polynomial in X, say P. And because ring homomorphisms preserve addition and multiplication and all that jazz, it must send F of P to P of R. But there, we've determined what F has to be. So this F will do the job, and it's unique because there's nothing else it could be, because we determined F by the fact that it preserves addition and multiplication and subtraction. So that's it. So that's an idea that has a lot of variance, but what I'm going to try to do is to categorify this result. So in other words, I'm going to replace rings in the story that I just told by certain categories that have a structure similar to that of a ring. So what the hell do I mean by that? Well, like the category of vector spaces, say complex vector spaces, and linear maps between them, that actually is a lot like a ring. It's a category, but it's like a ring. Why is it like a ring? Well, because we can add and multiply. We can take the direct sum of two vector spaces and get a new vector space, and that's like adding them. We just draw a stupid little circle around the plus sign to indicate that we're doing something categorified. We can also take the tensor product of two vector spaces and get a new vector space whose dimension is the product of the dimension of those two guys. And so that's like multiplication. And if you learn about this stuff, you'll learn that most of the usual ring axioms are true in this situation, except that they're true up to isomorphism. So like if I take the direct sum of two vector spaces in one order, it's not really literally equal to the direct sum in the other order, because this consists of pairs, something comma something, and this consists of pairs in the other order. But there's an isomorphism between them. So the commutative law, the associative law of multiplication, the distributive law, and the laws for adding 0 and multiplying by 1. Notice that C is the one-dimensional vector space. They all hold, but they all hold up to isomorphism. So that's what we expect in category theory. In category theory, we shouldn't expect equations between objects. We should just expect isomorphisms. That's what we usually get. So we're getting something that's like a ring, but it's a category where the laws hold up to isomorphism. So you could try to take that idea and define a concept of a two ring. Two means like right after ring. And we could try to define it to be a category that resembles a ring in the manner that I was sort of sketching out. But there's one big difference. There's no such thing as the negative of a vector space, or at least there hardly ever is. You can show that if the direct sum of two vector spaces is the zero-dimensional vector space, then they both have to be the zero-dimensional vector space. So the only vector space that has a negative with respect to direct sum is the zero-dimensional vector space. So subtraction is not going to work in this. So actually vect isn't really like a ring. It's really like a rig. So what's a rig? Well, if you remove the letter N from ring, you get the word rig. And so that's the idea. A rig is a ring without the negatives. So you subtract subtraction from your concept. And so what's a rig? It's a set R with an addition and a multiplication operation and an element 0 and an element 1, where it obeys all the usual ring axioms that don't mention negatives. So we don't have an additive group anymore because we don't have negatives. We have what you'd call an additive monoid, a commutative, well, it's commutative too, commutative monoid. So you can It's commutative and associative. Multiplication is associative. The distributive law holds on both sides, and 0 does what it's supposed to do when you multiply as well as when you add. So that's a rig. Rigs are running around all over the place. It's just our sadly deficient algebra textbooks that don't give them their due. Someday when I take over the world, I'm gonna make algebra textbooks talk more about monoids and rigs to bring them up to speed with the much beloved groups and rings. For example, the natural numbers are a rig, right? You can add them, you can multiply them, all the usual laws hold. The only thing that they're missing are negatives. So that an algebra textbook would have no theorems about the natural numbers. What is this stuff? Somehow it's like, oh, that's too simple. It doesn't have negatives. We're not going to think about it. But actually, there's plenty of theorems about rigs. And it's actually very interesting to see like what theorems about rings don't work for rigs. You got ideals in rigs, all sorts of stuff works, but it's not quite the same, but it's interesting. So the natural numbers are very fundamental. And they're sort of like the integers, but without negatives. So the integers are important because they're the initial ring. Given any ring, there's a unique homomorphism from the integers to that other ring, because it sends 0 to 0 and 1 to 1, and that determines it. Similarly, the initial rig is the natural numbers. Given any rig, there's a unique rig homomorphism from the natural numbers to that rig. So when we go over into rig land, anything you used to want to do with the integers, you should start wanting to do with the natural numbers, basically. So, for example, we could look at polynomials with natural number coefficients. So no negative coefficients, please. Natural number coefficients on one variable. That's what I'm calling n of x. And that's the free rig on one generator, just like z of x was the free ring on one generator. Right? So what I'm saying is, what does this mean? It means that give me any old rig and any old element of it, there's a unique rig homomorphism sending x to that element. The definition of a rig homomorphism is just what you'd expect. It preserves everything, the addition, multiplication, 0 and 1. And the proof of this is just exactly like the proof of the last one we saw. You can just see right away that any polynomial has got to get sent to P of R. So that's a little evidence that you can do math with rigs. But now what I want to do is to categorify. So I want to make up a concept of tworig, which is a category that's like a rig. And there are lots of categories that have a kind of addition and multiplication, like the category of sets does, right? You can take disjoint union of sets, that's like adding them, and Cartesian product of sets is like multiplying them. But today I want to focus on examples that are sort of more of a linear algebra flavor. So I already mentioned one, the category of vector spaces with its usual direct sum and tensor product. That's the kind of thing that should be a tworig in the definition I'm going to give. Or if you like geometry, something called vector bundles. So that's like you got a manifold, and sitting over each point in the manifold, you've got a vector space in a nice, smoothly varying way. You can take direct sums of vector bundles just by taking direct sums at each point of the vector spaces. You can take tensor products too. So that there should be a tworig of vector bundles on any given manifold. Then you've got examples of algebraic flavors, like the category of chain complexes of vector spaces. There's a way to take direct sums and tensor products of chain complexes. And again, it has the distributive law and all that jazz. Or the category of representations of some particular group on, say, complex vector spaces. You can take direct sums and tensor products of those too. So that's another tworig. And this type of tworig I'll be especially interested in, I guess. And this category Schur that I've just hinted at, it's going to be a tworig, and it's going to be a very special tworig. All these examples here are what are called symmetric tworigs. That is, they have something like the commutative law for multiplication going on. V tensor W is isomorphic to W tensor V, right? So not every ring is commutative, and not every rig is commutative. Not every tworig is symmetric, but we're going to focus in on the ones where this commutative law holds up to isomorphism. So the word for that is symmetric. Let's just look at an example. So rep G. So a representation of a group is a, let's say, finite dimensional vector space with a linear map rho of G from it to itself for every group element, such that if you multiply group elements and then convert it into a linear map, that's the same as doing it separately for each one and then composing those linear maps. Of one is the identity. And then you can talk about morphisms between representations. So if I've got a representation on V and one on W, then a morphism between representations is a linear map from V to W that has this nice property here that if you apply rho of G and then map over, it's the same as first mapping over and then applying psi of G. So when you study representations of a group, you're really studying this category where the objects are representations and the morphisms are these kind of morphisms here. And so that's this category rep G. Because there's a way to take a direct sum of representations or a tensor product of representations to get a new representation. And the formulas for how you do it are just these blitheringly obvious formulas that you would have guessed anyway, without being told. That's how you should do it. So that's an example. So the category Schur that I'm leading up to here, it combines the categories of representations of all the symmetric groups. Sorry, was that a?
Yeah, can I ask you a quick question? Are you
Sure,
going to give the abstract definition of tworig, or is that something?
Yes, I will. Yeah, I will.
Okay.
So
I'll save my questions then later. Okay.
Yeah, so I'm trying to get you to want it rather, right? So if you give someone something too soon before they want it, they don't like it. In math, at least, yeah. Right. Here's a machine you never knew you wanted. This is your birthday present, right? So, so yeah, I'm trying to build up some hunger for that definition. Yeah, and then you'll see why I put it off, right? So the category Schur is going to combine these categories of representations of all the symmetric groups in one big fat category, and it's going to do it in a pretty damn simple way. An object of Schur is just going to be a list of representations of all the groups Sn. 0, row 1, row 2, blah, blah, blah. But to keep things sort of finite, we'll say that all but finitely many of these representations rho n will be 0-dimensional. So the sort of total dimension of all these representations is finite. And then a morphism between such things is just a list of morphisms of representations, so between the first one, the second one, the third one, and so on. And then the way that we define direct sums is just sort of the obvious way. So, right, rho plus psi sub n representation in its list is just the direct sum of rho n and psi n. So there are different ways to think about this. You can think of a representation of SK as an object of Schur that's 0-dimensional except at k equals n, right? So an object in Schur is a whole big fat list of representations. But if we say, I want them all to be trivial except the kth one, then it's just a representation of SK. And so the representations of SK form a subcategory of Schur, where we just look at these lists that are trivial except at the kth entry. So this is the sense in which all representations of all the different SKs are sitting inside Schur. And then thanks to this finiteness clause in my definition of Schur, every object of Schur is just going to be a finite direct sum of representations of different SKs. That finiteness clause was this jazz here. So that's a way to think about it. So basically, we're just letting ourselves take direct sums of representations of different symmetric groups, and they will still make sense inside this big fat sort of umbrella Schur. Now, the tensor product in Schur is not defined component-wise. If it was, this would be boring, and then we would really not be doing anything. except studying all the representations sort of sitting side by side. This is the exciting part, the multiplication in our tworig. And it's going to be enough to define it on representations of symmetric groups. Because remember, every object of Schur is a direct sum of these guys that are representations of a particular symmetric group. And our tensor product is going to distribute over direct sum. So if I know how to tensor two of these guys, then I can figure out how to tensor anything in Schur and anything in Schur. So first, what you do is a sort of standard trick, which is there's some funky kind of tensor product, which I'm drawing with this box, which is going to be a representation of a different group, SK times SL. And that is given in just sort of a nice tensor product-y way. So rho box times psi applied to the pair of symmetric group elements GH is just rho of G tensor psi of H. And then starting from a representation of SK times SL, there's a way to cook up a representation of SK plus L. And this process is called induction. So it turns out it's a very general kind of thing. If you have so here you see we've got like this thing, this group SK times SL is a subgroup of this bigger group here. That's all that really matters. Whenever you have that story, you can take representations of your big group and restrict them to representations of the smaller group. You just say, hey, I only care what it does to guys in that subgroup. That's a very obvious thing. It's a functor. But it turns out that there's a process going back. It's called a left adjoint, an adjoint functor, which freely forms a representation of the big group, starting from a representation of the smaller group. So if you learn some group representation theory, you learn a formula for induction, for like concretely, what does it look like? But I don't think we even need to get into that now, so I won't do it now. I'll just say that there's like some nice, easy way to boost up to a representation of a bigger group called induction. And so I'll leave it at that. So that's how, starting from a representation of SK and a representation of SL, we get a representation of SK plus L, but all these categories, remember, are sitting inside Schur. So this is giving us a multiplication on a tensor product on the category Schur. Okay, so that's how Schur works. But now let me tell you what a symmetric tworig actually really is, and which is necessary for me to make precise my claim that Schur is the free tworig on one generator. So we've got to talk about the multiplication and the addition in our tworig. That is the tensor product and the direct sum in our symmetric tworig. So first, let me talk about the tensor product. There's a very general concept of a category with a tensor product. Category with a tensor product is often called a symmetric monoidal category. So it's a category that has a functor from it times it to itself, which is called tensor product, and a special object called the unit for the tensor product. And then it obeys the associative law and the left and the right unit law and the commutative law up to isomorphism, up to isomorphisms. So that is, there's a concept of a natural isomorphism between functors, and there's a functor that takes three guys in C and tensors them this way, and another functor that tensors them this way, and we're going to demand that there's a natural isomorphism from one to the other. And similarly for this left unit law and this right unit law and this commutativity or symmetry. There are some equations that these isomorphisms need to obey, which if you learn about monoids, you will learn. So there's a thing called the pentagon identity and so on. You'll notice that this text here is in blue. That's so that if you ever get a hold of these slides, you can just click on it and you'll get whisked away to see these equations. But I don't think I want to show you these equations now because we're not really going to prove much, so we don't need to get into them. But symmetric monoidal categories are running around all over the place. So like the the category of vector spaces with its tensor product is symmetric monoidal. The category of modules over a community is symmetric monoidal. The category of sets is symmetric monoidal with Cartesian product. Pretty much any kind of mathematical gizmo where you can multiply two of them, get a new gizmo, you're going to give you a symmetric monoidal category, most likely. So it's good to know this definition, because then you know that, oh, that's what I've been looking at all this time. So now what else? I want to get into a linear algebra kind of mood here. So I'm going to talk about linear categories. Those are categories where sorry, I may be freezing up here. I can't tell.
Yes, just a little.
Okay, just a little bit. Nothing interesting was missed. I gave the whole rest of the talk just then. So a linear category is a category where the set of morphisms from one object to another is actually a vector space. And composition of morphisms is linear in each morphism. So like vect is a linear category, right? You don't just have a set of linear maps from one vector space to another. You've got a vector space of linear maps from one to another. And composition is linear in each slot. So all sorts of categories I've been mentioning are linear, like rep G is linear. And then now I want to get the addition going on in my tworig. And so I'm going to look at what are called Cauchy complete linear categories. So those are ones that have nice direct sums called byproducts, technically, and a nice concept of a zero called a zero object. And I want every idempotent morphism from some alpha, when you square it, you get the same thing, to have a kernel and a co-kernel. So it's more likely that you will have heard about abelian categories than you will have heard about these guys. But abelian categories are much more powerful than these. They've got more stuff going on. So in an abelian category, every morphism has a kernel and co-kernel. But I'm trying to strip it down to the basics of what we need here. And one reason why, for example, is that the category of vector bundles is not an abelian category. A linear map between vector bundles doesn't always have a kernel, but an idempotent morphism has a kernel. So in other words, I'm just trying to say there are examples of things that are like this. And there's also some more technical reasons why this is like the right framework to work in, but take longer to explain. So basically, just think of this as like a kind of world where you can do some kind of linear algebra, basic linear algebra. Okay, now we're going to blend the addition and the multiplication. So a symmetric monoidal linear category is a linear category that's also symmetric monoidal. And then the tensor product of morphisms should be linear in each argument. So that's combining the linearity and the symmetric monoidal. And then finally, a symmetric tworig is a symmetric monoidal linear category that's also Cauchy complete. You might be a little surprised that I didn't demand that the tensor product get along with the byproduct in some manner. Normally, when you combine two mathematical gizmos, you got to say some extra stuff about like how they get along with each other. But one cool thing about this Cauchy completeness is that it automatically gets along with the tensor product. If you learn more category theory, you'll say that, oh, these guys are absolute colimits. They just get along with everything. So that's a technical virtue. Yep.
Sorry. Yes. So now let me ask a few questions, if that's all right.
Sure.
So if I just want a tworig, then I just remove symmetric, right, from the adjectives.
Yeah, that's right.
Yeah. So I was going to guess that it was just going to be a monoidal linear category which admitted finite direct or byproducts, but somehow now you're also doing idempotent completion. So is
right.
there an easy, somehow that kind of snuck in the back for me. Why are you doing that?
We really want to do it. So Well, so like when we, yeah, so why do we want to do it? So at the end of my grad student talk, I was showing how Young diagrams also give you representations of things like SUN. And I was doing some stuff like I was saying, take some vector space like C2, tensor it with itself. That's something you can do in a tworig. You can tensor things. And then the symmetry group will act on that tensor product with itself. Well, that would happen when you have a symmetric monoidal linear category. And then I said, oh, but I want to look at the symmetric tensors, the tensors that are invariant under that. That would be a subspace of that. And that's where we need to be able to take a co-kernel, or you could think of it as a kernel in either way, in fact. So to be able to like pick out the symmetric parts of things, we want that. Yeah.
That's great, thanks. And then the other thing that I was going to ask is, so rigs don't form a two-rig. All the collection of all rigs aren't going to form a two-rig because of the linearity. Is that?
Yeah, that sounds right. Yes, I mean, if you did algebras, like, which are, yeah, algebras over the complex numbers. I'm using a ground field of the complex numbers whenever I say linear here. So I'm like saying, hey, I want to do complex math. So instead of talking about rigs, it would be more to get into that framework. You'd want to do something like algebras over the complex numbers, and they would indeed form a two-rig, if I'm correct. Yeah, that sounds right. Yeah, I think that's right. Yeah. Let's see, is that right? Is the kernel of a algebra homomorphism and algebra? Yeah, I think so. I'm just making this up, so I might possibly be wrong, but you were sort of asking like, why don't rigs form a two-rig? Well, it's because I'm choosing a two-rig that is biased towards getting the complex numbers into the game. I didn't have to do that. If I was just developing the whole general theory of two-rigs, I would have not demanded that their linear categories were I mean vector space over the complex numbers. But I'm not really trying to do the whole theory of, there's quite a variety of things you can think about in this game. And I'm not trying to do that. I'm just trying to focus on things that are connected to representations over the complex numbers. So yeah, that's what the reason for the mismatch.
Thanks so much.
Sure. Right. So that was the symmetric two-rig. Now I hope you see why I didn't start out by telling you this stuff. You would not have liked it at the beginning of the talk. So then to say that Schur is the free symmetric two-rig on one object, we got to know what maps are between these things. And I'll sort of whiz through that. So the right kind of map between symmetric monoidal categories is called a symmetric monoidal functor. So it's a functor that preserves tensor products up to a natural isomorphism and preserves the unit up to a natural isomorphism. And these need to obey some equations. Again, you could click on that and see what they were. A linear functor is a functor between linear categories that's linear on the Hom sets. So if f and f prime are morphisms going from some object to some other object, you could take linear combinations of them, and f has to preserve that linear structure. So then that's it. So a map between, I'll just call it a map for short, a map between symmetric two-rigs is just a symmetric monoidal functor that's also linear. It will automatically preserve the byproducts and the zero object and everything else that the two-rig has. So we don't need to say anything more, luckily, because the slide is full. So then our theorem says that if you've got any symmetric two-rig and any object of it, there's a map of two-rigs from Schur to R, which sends X, some special object in Schur, to R. What is this X? I never said what this X was. Well, it's sort of the most, It's a very simple thing. It's just the one-dimensional representation of the group S1. So it's not quite zero-dimensional, but it's not the simplest thing in Schur, but it's like the second simplest thing in Schur. And moreover, F is unique. It's unique up to, there's something called a symmetric monoidal natural isomorphism, which is the right kind of notion of isomorphism between maps of this sort. And so that's all we should expect in category land, is that F is unique up to that kind of isomorphism. So that's the theorem. Actually proving it takes a fair amount of work, and I won't really get into that, I think. I don't think that will make any of us much happier right now. I'll just say one kind of thing. So like, suppose we are in this situation, so right, so we have this F that sends our favorite object in Schur to R. Well, then it should send every object of Schur to something in this tworig R. And so then you should ask, like, okay, what is it? Right, but way back here, oh no, I'm going to regret this, but okay, like here, right? So we said F sends X to R, then what does it do to any other polynomial? Well, it does something pretty reasonable to every polynomial. So it's a question that's sort of important because it's how you prove that this theorem works, is to understand what F does to everything in Schur. So that's the question I'm asking here. I'm calling the objects in Schur rho because remember, they're lists of representations of all the symmetric groups. So what is it? Well, luckily there is a concrete formula for it. So suppose rho corresponds to this list rho n of representations of all these different symmetric groups on a bunch of different vector spaces Vn. Then here's what f of rho is. So what we do is we take our object R, we tensor it with itself n times. That's called the tensor power. The symmetric group Sn will act on our tensor n by permuting the factors in the tensor product, which is the kind of stuff I was starting to talk about at the end of my grad student talk. So Sn acts on our tensor the n. But because linear combinations of morphisms are morphisms, the whole group algebra C of Sn acts on our tensor to the n. This is linear combinations of group elements. But also, Vn is a representation of Sn, because I just said rho n is a way for Sn to act on Vn. So this group also acts on Vn, and so the group algebra also acts on Vn. And so what we've got here is a left module of this algebra C of Sn, and I'm being a little sloppy, but you can check. It's really, you can make it into a right, this guy into a right module of the group algebra C of Sn, because any left module of a group algebra can become turns into a right module. That's how it works. And so we can tensor over that, and we actually get, it turns out, an object in R again, and then we add them up. Now this formula here, if you've got a good imagination, it should remind you of a Taylor series, or something like a Taylor series, or a polynomial perhaps. And indeed, it's exactly like what we had in the simpler situation. So like if you have a homomorphism from Z of X to a ring R, and you know what X goes to, some element R of your ring, then you know what it does to any polynomial. You can write any polynomial out, write it out in gory detail, and then f of p, well, I said before that it's p of x, but what is p? Sorry, I said before that it's p of r. Well, what is p of r? Well, it's this. We're applying this polynomial to our ring element r. So this formula for how, sort of an explicit formula for the homomorphism f, we're just copying it over at a higher level, so to speak, to get this formula for the functor f. So these coefficients here were integers, and now here they are basically vector spaces. They're vector spaces on which the group acts. And here we're taking a ring element and multiplying it to the nth power. Here we're taking an object and tensoring it with itself n times. And this plain old sum is turned into a direct sum. So we're really just taking a pretty simple idea from algebra and knocking it up one level, basically just drawing circles around all the plus signs and the times signs and getting a much more deep result, a deeper result. So what I'm trying to hint at here is that there's some analogy going on between rings and tworigs, and between polynomials on one hand and Schur functors on the other hand, and so on. And you could try to sort of keep extending this. And what you're doing in a way is you're categorifying commutative algebra, taking concepts from commutative algebra and saying, that was fun, but then everything was just a set. Now I want to have it be a category. So I'll try this new stuff. And so when you do that, you run into some familiar things, familiar to some people anyway, like Schur functors, and hopefully also some unfamiliar things. Okay, I think that's it. I think I'll quit here. Hopefully there'll be some questions.
Hi.
Hi.
You asked me to ask a question at the graduate student part, and I kind of disappointed you, but I'm back.
Okay, good. You've got a second shot.
So if I think about the category of rings as enriched over sets, then the free ring on one generator represents the underlying set functor.
Yes.
Is the same true for in this case? And this, I kind of want it to be some sort of underlying category thing, but I wasn't sure if I should add. I was looking at this theorem, or I guess in the
great question
afterwards.
Great question. Yeah, that's actually something that a step in our proof is that we showed. I'll slowly answer your question, but the first thing is yes. So that this free tworig on one generator, we show that it represents something, and it represents the underlying linear category. Am I getting this right? Yeah, the underlying linear category functor. Right. So maybe I can switch over to my crummy handwriting and draw something about that. So yes, here we are. So yeah, so there's, let's see if, so, right. So what we're saying is that, what I'm saying here is that if you have any symmetric tworig, sorry, I'm doing it backwards. Sorry. If you have any symmetric tworig, you could look at maps symmetric tworig maps from Schur to it, and that will be equivalent as a category. So there's a category of these things now, because there are these maps and then natural isomorphisms between these maps. And that will be isomorphic to what I could call like U of R, the underlying, where U is the thing that says, you give me a symmetric tworig, and it will have an underlying linear category. So there's some two, yeah, something like that. So yeah, so that's all supposed to be a fancification, a fancy version of something like this. If I had a commutative, if I had a ring, a set of ring homomorphisms from Zx to R is isomorphic to U of R, where, to be a little bit pedantic, U of R is the underlying set of the, sorry, I just did something terrible. Sorry, I can't see what I'm doing here. Yeah, U of R is the underlying set of that ring R. I'm struggling to. So that's right. And in fact, we prove this thing first as a step towards proving the theorem that I stated. So this turns out to be like the right way to go about it. So that's great. Yeah. That is, we prove this.
I guess.
Mm-hmm.
I guess the question is, how many adjectives can you add to? I don't know what kind of object Schur like Hom of two rigs is. Maybe it has some sort of monoidal or braided structure on it. And if that's the case, can it just represent an underlying, like, could I add, say, monoidal to both sides of this? Or is this as far as it goes? This is maybe not super well posed.
Well, it's fine. I mean, of course, yeah, let's see. So of course, in most of my work on this, I've not been trying to add adjectives. I've been trying to subtract them because I'm trying to strip the theorem down to its bare bones. But there's not, it's probably better to think about this case first. So like one thing that you learn right away, for example, is that like the set of ring homomorphisms from a ring to a ring is not a ring. You can't multiply ring homomorphisms and get another ring homomorphism. So I think that sort of kills off one of your plans there of trying to say that, like, hoping.
I could put a Abelian group here in the bottom, right? Am I about to, did I just say something dumb? Yeah, I could put a Abelian group there, right?
Well, it wasn't dumb, but it was still wrong because you can't even add ring homomorphisms and get a ring homomorphism. Right. So
it has to send one to one.
Because it has to preserve the
modules,
multiplication.
I guess, for that. Right.
Yes.
Okay.
Yeah. So you lose. So I don't think there's much you get there. Yeah. In some other similar games, you would get a lot, right? So if I wasn't like, if I wasn't looking at things here that had to preserve the multiplicative structure, the tensor product structure. If I just wanted them to preserve the linear structure, that is the Cauchy complete linear category structure, then this thing would be a Cauchy complete linear category. So just like, like map, if you look at Hom from an abelian group to an abelian group, that Hom is again an abelian group. Yeah, so there are many variants on your question where you could get some more structure on this U of R, and in the basic case down here, and then for all of those you could try to copy it up here, and it would tend to work. Mm-hmm. Yeah, I will say the direction that we've been going in digging into this further is we've been thinking just a lot about Schur itself, that one particular guy, and that the Schur turns out to be has a lot more structure than just being a tworig. It turns out it's something called a two-bi-rig. So it has not only a multiplication, it has a co-multiplication and a co-addition. And then it's something even better than that. And so it turns out that all these extra features that Schur has play a big role in the representation theory of symmetric groups. So people have learned that that there's like tons of things you can do with Young diagrams, with names like plethism and so on. And what we've been trying to do is to sort of get a more conceptual outlook on what all that stuff is coming from. And basically it's all coming from like extra structure that this tworig has. And so that there I could throw adjectives at you all night long for what the structure it has. But in general, I don't think this thing has huge amounts more structure. Yeah. Yeah, thanks. That was a really cool question. Yeah.
Thanks a lot.
I had one further question. So I'm familiar with, I guess you defined, I think, Well, you've done a number of things like this, like two Hilbert spaces, and I'm familiar with, say, two vector spaces, where you want to keep going, right? You want to figure out what
That's
the higher.
right.
Well, so
Oh, sorry, you mean keep going in the n
yeah,
categorical
like,
direction.
should I be?
As you
Are
can
you?
see, I'm mainly keeping going in a horizontal direction.
I see.
I just do
Yeah.
to this, to that, to the other thing. Yeah.
Should I be
But
asking
yes.
what a three-rig is, or is this something that is the wrong question at this time? I guess is the.
Well, it's not a question that I'm currently thinking about. So my own yes, all that kind of further categorification should be very, very interesting stuff to think about. The reason why the symmetric groups were showing up for us, and in particular the reason why they were sort of showing up en masse, sort of all together, is that there's this thing that I like to call S, which is the groupoid of finite sets and bijections. It's the category of finite sets and bijections, but everything is invertible, so it's a groupoid. And this has all the symmetric groups sort of sitting inside it. But the reason why it's interesting to me, the reason why it sort of shows up here, is that this is the free symmetric monoidal category on one object. So the idea is you take this object, bloop, and then you start tensoring it with itself, bloop, bloop, bloop. And then you say, okay, what kind of morphisms do I get? Well, if all I know is that I have a symmetric monoidal category, then the only kind of morphisms I can really get are morphisms where I'm like switching two things. And so the kind of morphisms I can get would be things that could look sort of like this. Well, it's a pretty boring one, but it's a permutation. So we see that so we get all finite sets and all bijections between them by this method. And so what we're doing when we're forming the free symmetric two-rig on one generator is we're taking this S and then we're throwing in the extra structure. We're throwing in the structure of it being a linear category, and we're throwing in these direct sums and these kernels and co-kernels. So we're first turning this into a linear category, and then we're doing this idempotent completion, as you put it. So to answer your question, then, if you're going to try to do like three rigs or something like that, what's the free three rig on one generator? The place to start would be down here. That is, before you throw in all the linear structure, just think about the sort of the multiplicative structure. And so you'd want to know, like, what's the free symmetric monoidal two category on one object? And yeah, I actually don't think that is tons more interesting than this. I think it would be a whole lot like this. I think. I think it would basically be equivalent to this. But there are variants where you could get much more rich and complicated things. If you threw in more than just one object, you could get some more fun stuff to happen. But then there's the whole linearization business. If you're trying to look at the free symmetric three rig on one generator, you need to decide what you mean by three rig, what kind of linear structure you're putting in. But you might get something like representations of the symmetric groups on two vector spaces showing up instead of on vector spaces. So since you have heard about two vector spaces, I don't mind saying that word. So yeah. So basically what so all that could be very interesting to study. So right now what I'm sort of currently in the mood for is sort of a horizontal exploration of different branches of mathematics and what happens when you categorify them once. Because you very often get things that people have already studied but just haven't known that that's what was going on. But then if you go higher vertically to higher n categories, then you actually often get to things that are more novel And well, homotopy theorists tend to have studied a bunch of those things already, but far fewer people anyway have gone up in that vertical direction and seen what's up there.
Thank you so much. I appreciate it.
Sure, yeah.
Any more questions for our speaker? Then let's thank John again. Thanks so much for that wonderful talk.
Great, thanks a lot. That was a lot of fun. I'll see you folks. So you said, I guess there's a video of this thing is going to show up somewhere. If you have any desire to link it to my slides, I can provide you with a link to my slides. And,
that would be lovely. Thanks so
yeah.
much.
Yeah.
Like that. Thank you.
Okay. Okay.
Great.
See ya.
Yeah.
See ya.